Hello friends, I'm a cloud solutions architect at Microsoft and my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting lead code problem called Game of Life. Now, if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, Google, DoorDash, Microsoft, Snapchat and Facebook. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a lead code medium problem and also very well like problem on lead code. Basically, we need to find the next state in the game of life. Now the question is, what is game of life? Originally this has been created by a mathematician named John Horton, where we are given a board that is made of m cross n grid. So there can be like any 2D grid of m cross n cells. Now the thing is, we are given the initial state of a cell, and the possibility is that any particular cell can be a live cell, so that is represented by value number 1, or it could be a dead cell that is represented by value number 0. Now the thing is, we are given the original cell in some formation, and then we need to find the next state of the cell using the rules that are provided by the game of life. So over here I am basically creating a table from these four given rules, and then we are going to use this table to see that what would be the next state in game of life and how would we be able to solve this problem. Okay, first one is, it's saying that any live cell with fewer than 2 live neighbors dies in the next state due to the underpopulation. Okay, so if the current state is live, so we just note this with value number 1. Okay, so if the current state is live and if the number of neighbors is less than 2, okay, so the number of neighbors is less than 2, then the next state is going to be 0, or the next state is going to be dead state. Now the next one is that if any live cell with 2 or 3 living neighbors will live on to the next generation. Okay, so if the current state is 1, if the number of neighbors is either 2 or 3, if that is the case, then the next state is going to be live for that particular cell. That is good. Now the next third one is that any live cell with more than 3 live neighbors would die due to overpopulation. So okay, if the current state is live and if the number of neighbors is greater than 3, if that is the case, then basically the cell is going to die and the next state is going to be 0. And the last one is that if any dead cell with exactly 3 living neighbors would become a live cell because of reproduction. So if the current state is going to be 0 and if the number of neighbors is exactly 3, then the next state is going to be 1 for that particular neighbor. These are the only 4 rules that we are concerned with for our game of life. And initially we would be given an example that looks something like this, where on an m cross n grid we are given some values that represents live and dead cells, and we need to find the next subsequent states based on these 4 rules. So this is the whole ask of the problem. Now let's try to see some examples. So if we see this first example, okay, let's see that what would happen with each cell. So currently the position of this cell is 0. Okay, this is a dead cell. Let's see, for dead cell, does it has 3 neighbors that are alive? No, that is not the case, which means this will remain dead. Okay, so this will remain dead. Now for this next particular cell, okay, currently this is live one. For the live cell, how many live neighbors this has? This only has 1 live neighbor, which means it is less than 2 live neighbor. So this would also be dead. So this is going to be dead. Also for this one, this is already dead, and again it will remain dead. And also this one will this one. Okay, so this is the important part. Now at this particular position, we do not need to see the positioning of the neighbor from this particular cell. We need to see the positioning of live neighbors from this original cell. So this is important for this problem. So even when we are at this position number 1 and we need to identify that how many number of live neighbors this has, we are going to refer over here, not on this newly created state, because all the states are going to change at the same time. Here I'm showing you one by one, but in originality it's going to happen everything at the same time. Okay, so in this case, currently this one only has 1 live neighbor. So again, this one has less than 2 live neighbors. So since the number of live neighbors is less than 2, this is also going to become 0. Now let's try to solve for this next problem. Okay, in this next one, okay, this one looks very similar, so I'm going to add one more 1 over here. Now in this case, okay, currently this one is 0. Let's see that how many live neighbors this cell has. This cell currently has 3 live neighbors. Okay, if there are 3 live neighbors, which means that this 0 state has the possibility to become state number 1. So in the next state, this is going to become value number 1. Okay. And in the over here, now this one has 2 live neighbors, not 3 live neighbors. We are not considering this portion. We are only considering the original pattern. So currently this one has 2 live neighbors. If there are 2 live neighbors, it will remain 1. So this will remain 1. Same goes with this one. This has 2 live neighbors. So this will also remain 1. And same goes with the last cell, that the last cell also has 2 live neighbors. So this is also going to remain 1. And this is going to be the next state. Let's try a little bit trickier example. So in this case, let's see that what is going to be the answer. And this is going to be the next state. And this is the whole crux of the problem that we need to solve. Now, understanding this problem is more trickier than actually solving this problem, because the solution for this problem is actually quite simple. And there are only like just few things we need to consider to make this more efficient. Okay, so now we have our example that we are going to use to solve this problem, and we have the number of rules that is already given in the problem statement. And now let's see that what is going to be the solution. Now suppose if we want to solve this problem, what are the things we are going to need? Well, first thing we are going to need is that for every single cell we are going to need the number of live neighbors. Okay, so we would be able to calculate that using just going over the grid, but in the problem we would be able to do it quite efficiently using just scanning through all the neighbors of any particular cell. So that is not a difficult task to do. Now let's see that what would be the solution. Now suppose we are at this particular position 1. Now how many number of live neighbors this has? This one currently has 2 live neighbors. Okay, if there are 2 live neighbors, this one is going to remain 1. So we don't need to do anything. Let's just keep this 1 as it is. Now for this particular one, this has 3 live neighbors. So again, we are going to use this rule. So this one is going to remain as it is. Now for this particular one, this also has 2 live neighbors. So we don't need to do anything. This one can remain as it is. So currently this upper row is going to remain as it is. Now for this particular 0, now this 0 is actually covered with all 3 ones, which means that this 0 needs to become a value number 1. Okay, so now this becomes value number 1. Now when we are at this position number 1, how many number of live neighbors does this particular one has? Well, okay, let's count. This one has 1, 2, 3 live neighbors. Okay, 4 live neighbors and also 5 live neighbors. The question is, can I call for this particular cell that it has 5 live neighbors? The answer is no. Why no? Because this particular one was originally a 0, and hence this should only have 4 live neighbors, not 5 live neighbors, because this cell I changed while I was iterating over. Now this is a problem that we have to worry about. And what is happening is that while we are iterating over the matrix, we are changing the state depending on these 4 rules, and it could be possible that the rules that are being changed could impact the remaining cells on their rules, and we might end up with a wrong answer. So one possible solution for that is that rather than making changes in place, if we just create a duplicated grid for this particular cell which contains the original items. So say for an example, suppose this was the original input we are given and we need to make changes. So what we are going to do is, first of all, we are going to create a duplicated entries and we are going to keep track of live neighbors. Okay, so let's just first quickly create a duplicated entry. If I create, okay, so now I have created a duplicated entry, and now whenever I have to make the change, I'm going to make change in this original box. But in order to find that how many number of live neighbors exist, I'm going to check on the box with the previous state. So this is going to be the copied version and this is going to be the original version. And after I'm done making change to all the original items, basically all I will have to do is just copy them over to the copied version, and then I would be able to calculate the next state of the original version. So that is how I'm solving the problem of state changing by creating a duplicated entry. Okay, and now this becomes very easy. How very easy? Okay, so we already iterated over this first row. The values are going to remain 1 1 1. That is common, that is good. Now we are at this current 0 position, so this one has 3 live neighbors, so definitely this is going to become 1. Okay, awesome. Now currently I'm at this particular position 1, and the number of live neighbors is, it has 4 live neighbors. So because it has 4 live neighbors, it has greater than 3 live neighbors, this would become 0. So that this I can make change over here, that this would become 0. For this particular 0, how many live neighbors it has? It has 1, 2, 3 and 4 live neighbors. And now see over here, because I have this copied version, I was able to come up with the value number 4. If I was checking previously, I would have come up with the value number 3, and then I would have changed its state to 1. But actually, since this has 4 live neighbors, I would not need to do any changes to the state of this particular 0, and I can keep it as it is. Now I'm at this particular position 0. Okay, so for this 0, how many ones it has? It only has one neighbor, so I don't need to do anything. For this particular 0, how many neighbors it has? It currently has 2 neighbors, so I don't need to do anything. For this particular 1, how many neighbors it has? Currently it only has one live neighbor. Meanwhile over here it shows 0, but actually it has one live neighbor, so the number of live neighbors is less than 2, which means this state is going to be changed to value number 0. So let's see that from this particular original version we had, how many items got changed. Basically this got changed, so this became 0. This also got changed, so this was originally 0 and then it became 1, and this got changed. So this is how we would be able to solve the problem of game of life, just if we just create a copied version, and then it becomes very easy for us to find the live neighbors. Now the question is, your interviewer is directly going to jump onto you saying that if we see time and space complexity for this approach, the time complexity is going to be big of m cross n. Why? Because we need to iterate over the entire grid to calculate the result. That makes sense. But if we see space complexity, the space complexity is also going to be big of m cross n. Why? Because we are using this additional space to create a new copied matrix. And your interviewer is directly going to jump and saying that, can you solve this problem with big O of 1 space complexity? Can you do that? Okay, now let's see that how can we solve this problem using the constant space. For that, we are going to do some few modifications. And what are the modifications we are going to do? Well, first we will have to understand that what are the items we need. For any particular cell, we need the information of number of live neighbors it has, okay? But we need this information on terms of like number of live neighbors in the original state. So now what would happen is that if we are at this particular position 0, this 0 would be changed to 1, and then when we come to this position, then we will try to find that how many number of live neighbors in the original state it had. Then we don't need to consider this particular value, so we need a way to somehow store its original state, and this can be done pretty easily. How? Basically, currently we are dealing with integer values over here, so rather than using zeros and 1, what we are going to do is we can also use -1 and value number 2. And what would this -1 and value number 2 would represent? Well, it would represent is that if, say for an example, if the current state is 1, okay, so currently it is alive. Okay, if the current state is 1 and somehow it becomes dead, then in that case, rather than this 1 would have been converted to 0, we are decreasing the value, but rather than putting this as 0, we can actually put this as -1. And what would that do is, okay, so that means that this -1 should be dead. This is like we are using it as a placeholder, but this -1 would also indicate that the original state for this particular cell was actually 1. So when we are counting the live neighbors it originally had in the previous state, we would be able to calculate. Same way, if we are in a position where a dead state comes to life, so dead becomes alive. If that happens, in that case from 0 to, rather than going to 1, we would directly go to position number 2. And that is also another way that whenever we identify value number 2, we would presume that originally that was not live in the previous state whenever we are calculating the next value. So if we need to do that, we need to make some changes to our rules. And what is the change we are making? The change we are making is that anyhow, if the current state is live and if the next state needs to be dead, in that particular case, this is where we are going to put -1. So because this becomes dead, we are going to put this as -1. For this particular case, 1, if there are 2 and 3 live neighbors, this is going to remain 1. So we don't need to do any changes over here. For this particular one, if the number of neighbors is greater than 3, which means that this 1 would die. So this would also become -1. And for this particular 0, if the number of neighbors is 3, so in that case, this would become alive. So we would change the value to 2. So these are few rules we are changing. And now let's see that how can we make the things work out in place without using any additional memory. Okay, so this particular row we are not changing because we are implementing this particular rule. Now we are at this position number 0, so this 0 needs to be needs to bring back to alive. So if this is coming back to alive, rather than making this alive with value number 1, we are actually going to mark this as value number 2. So this would also indicate that if the value is 2, then the original state was 0, and this is going to be very helpful. Now we are at this position number 1. How many number of live neighbors it has? Okay, so currently it has 1, 2, 3 and 4 live neighbors, not this one, because the value is 2, which means that the previous state was actually 0, so we are not considering that. So since this has 4 live neighbors, so greater than 3 live neighbors, this needs to die. If this die, we are going to use this as -1, so that is going to be helpful to us in the future. So this becomes -1, which would indicate that the original state was actually 1, and this is going to be helpful. Now we are at this position number 0. How many number of live neighbors it has? So it currently has 1, 2, 3 and also 4 live neighbors, not 3, 4 live neighbors, because this 1 used to, this -1 represents that this used to be originally 1. Okay, so this would remain 0. Now again, for this particular 0, how many number of live neighbors it has? So currently it has, okay, so this was originally 0 and this was originally 1. So this only had 1 live neighbor, which means this would remain 0. Same goes for this one. This particular 0 has, okay, 1 live neighbor and also 2 live neighbors. So if there are 2 live neighbors, we don't need to do anything. And for this particular one, how many number of live neighbors it has? It only has 1 live neighbor, which was this value number -1. So this is going to turn out to value number 0. But rather than turning to value number 0, we are going to turn it to -1. And this is going to be the next state. Now, once we get this next state, this is not the answer we need to return, because for our game of life, we need to return all the cells in either 0 or 1. Either they are dead or they are alive, nothing more than that. So in that particular case, what we can do is, if at any point we identify the value to be like positive, so in this case this 2, so this needs to be converted to value number 1, because this indicates that this one is alive. And if we find 0 or negative value, which means that that one is dead, so in that case we will make these changes. So these two are going to become zeros and this one is going to become 1, and this is going to be the next state, and this is the whole solution. See how beautifully we are able to change everything by just simply making few changes to the input rules. And now if we see time and space complexity, in this case the time complexity is actually going to be big O of m cross n, because that is the grid size we will have to traverse. And if we see space complexity, the space complexity is going to be big O of 1, because apart from using like few variables, we are not using any additional space, and this is a very beautiful solution. Okay, so since this is already a pretty long video, I'm just going to explain you the code, and then I would post this code in the solution, so you would be able to check it out from there. Now, if we see, okay, initially we are initializing an array called neighbors, where we are adding the value 0, 1, -1, and this is going to help us navigate through neighbors of any particular cell. At the same time, we are getting the values of the row length and column length. So these are the values of m and n inside our grid. Now, first of all, we are creating two for loops, one inside the other, where this would allow us to iterate over the given input matrix cell by cell. After that, we are originally initializing a value of integer live neighbors, because this is the most important thing we need to consider, that how many live neighbors any particular cell has. And this is exactly what we are going to do next. We are going to run two loops, but this is going to be a finite number of cases we need to do. So this is not going to add any additional time complexity to our problem, but this is going to allow us to iterate over our neighbor. We are using this condition so we do not go out of bounds. And then at any given position, if we find that any particular neighboring cell has value number 1, then we are going to increment the number of live neighbors for that particular I and j positions. So this, okay, so this part gives us the number of live neighbors. That is pretty awesome. After that, now we are going to implement our 4 rules that we have established. And for these 4 rules, remember, first of all, we are going to check that if the given cell value is, if that is dead or alive. If the given cell is alive, then we are going to check that whether it has the number of live neighbors less than 2 or greater than 3. If that is the case, then the cell needs to die. And if the cell dies, we are going to change the value from 1 to -1. And if that is not the case, we will check that if the given cell is actually dead. If that is the case, which means we are going to check that if the number of live neighbors is exactly 3. If that is the case, which means the dead cell needs to be alive, and then we need to change its value from 0 to 2. So basically, this particular for loop is going to allow us to get all the values of the board setup with all the cells positions changed from either 0 to 2 or from 1 to -1. After getting that, all we need to do is just iterate over the given matrix again, and then simply check that if at any point we identify the value is going to be greater than 0, or the value is going to be either 1 or 2, which means we will need to convert that value back to 1, or else all the remaining values are going to be 0. And this is the whole solution. Pretty sweet and efficient, both in terms of time complexity and also in terms of space complexity. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which is pretty great. And I will be posting the solution in the comments, so you would be able to check it out from there. Also, there is one more place if you want to check all the coded solutions for many of the LeetCode problems that I have solved. And this is the GitHub repository that I have made public, that I will be posting this link in the description and also in the comments, so you can check it out from there. Let me know what do you think about this problem, and if there are any problems you want me to solve in the future. Thank you.